All right, so the handout I've given you, let's consider the case of a reservoir connected by a pipe to a fountain. And we've seen this picture before in class where there is a given water surface elevation. The pipe characteristics are known here, like we know the length and the diameter of the pipe. And then we also are given the elevation of the fountain downstream. So if we were to just simply use the hydrostatic equation, we could calculate the pressure of the water at the fountain with delta P is delta H times gamma. Delta P is delta H times gamma. All right, now these are traditional units. And so, for example, we're going to be discussing the delta H in terms of feet. So if you've got a calculator, let's calculate the elevation difference between the water elevation in the reservoir and the fountain. So that's 675.47 minus 588.36. So the delta H is 87.11 feet. Now, does anybody remember what the unit weight of water is in traditional units?
62.4 pounds per cubic foot.
Very good. 62.4 pounds per cubic foot. 62.4 pounds of force per cubic foot. So the reason why we're doing this on the board to begin with is we're using a new tool today. We're going to use EPANET to simulate some different scenarios. And whenever you use a new tool, you want to make sure that it can do things the way that you expect it to. So if we have a known answer for the pressure change that we determine with the hydrostatic equation and have on the board in front of us, then we can compare it to what is being predicted by the software. Okay, so let's just multiply that together. 87.11 times 62.4. Okay, now what I get from doing that is 5436. And what's the units? This is a change in pressure. And what are the units in this pressure change? Pounds per foot squared. So pounds per square foot. And a square foot, depicted here on the whiteboard, would have 12 inches in length, 12 inches in height. So how many inches squared are there in 1 square foot? 144. So if there's 5436 pounds of force in a square foot, how do we determine the number of pounds of force in a square inch? What's the conversion factor to get PSI from this? What is it?
Multiply by 144.
Would we multiply? Think about it. We've got 5436 spread out over all of these inches. So any one given inch is going to have less than all of the inches. We divide, yeah. So divided by 144 inches squared per foot squared. Okay, so do that if you've got your calculator handy. 5436 divided by 144. I get 37.75, and I'm going to write that as PSI, meaning pounds per square inch. Okay, so now we've solved this hypothetical setup just using the hydrostatic equation. And we're going to use that as a reference when we try the same setup using today's software. So you can get EPANET by going just to Google search. If you Google search EPANET, it'll take you, the first result here is the program page for this software. So if you've got a computer, go ahead and fire it up. Go to your search bar, search for EPANET, and as you scroll down, the top two results, one of them is an installation program for the software, and the other is non-installing. And the difference being that if you use the installation program, it goes into your registry, your Windows registry, and if you search down here, it would show up as a program in your list of programs. But if you don't have administrative rights on a certain computer, if you're just borrowing someone else's machine, you could put this other one, this non-installing software, like onto a jump drive and just run it off the jump drive without actually installing it onto the computer. So I'm going to choose that option just to illustrate that the software runs fine even when it's not fully installed. So click on that, it downloads it, and when you click on this, here are the different files that are inside of that archive. A zip file is kind of a compressed archive that brings together multiple files, and then it finds ways to compress it so that the end result is smaller than each of the files when they're uncompressed. So you can't run the software from this compressed environment. You have to extract it. And across the ribbon on the top here, you see how it's highlighted in pink, this word extract? So we're going to extract all, and I'm going to tell it to put it in a certain folder. I'll create a folder that's EPANET. Alright, so it's going to extract all of these files to a folder in this temporary. You could put it in My Documents, you could put it in your downloads. I've just created a temporary folder on the C drive that I know I'm going to be able to browse to later. It's just a location that I can easily find. So I click extract, and it really quickly extracts. We've got some examples, a help file, a tutorial, but what we're going to run here is the executable, this application. So if you click on EPANET 2W, then it'll start up the program. All right, so what it essentially is it's similar to a CAD environment where you're looking down from above and you're going to be drawing a pipe system as a schematic from a top view. And in the ribbon across the top here, it has a series of different icons that represent different things you might find in a pipe network. So we're only going to work with 3 of them today. We're going to work with this reservoir icon, we're going to work with the junction icon, and then the pipe. Those will be the 3 things that we do. Because remember, what we're simulating is a reservoir connected to a pipe, and then at the end we have a junction there so that we can understand the properties of the fluid at the junction. Okay, so starting off with this reservoir, click on that, and it changes your cursor when it's down in the network map to like what looks like a target icon. And so you'll also notice at the bottom that it's giving X and Y coordinates. So as you move the cursor around, the location that you could drop this reservoir icon could be representative of some coordinates that you have on a map. If you were working in a project that's in the real world and you wanted to have scaled distances and actual locations that match up with map coordinates, then you could be sure that you click in the right spot, or you can change the coordinate locations later on in an edit box. But let's just drop it anywhere. So click somewhere on the map, and we've dropped this reservoir. And so what we're doing is we're creating like a schematic representation of this system from the top view. So here's the reservoir. The next thing we'll do is a junction. Now remember, since this is a top view, if I click the junction over here and connect it with a pipe, it's not like the water's flowing uphill. It's just that the water is flowing in the northeastern direction. Or if I have the junction down below the reservoir, it's not like below it from a side view perspective. It's just up is north, down is south. So I'll just click anywhere. So here's my junction. And then the final thing I'm going to do is I'm going to connect those two locations with the pipe. So click on the pipe icon, and starting at the reservoir, click once at the center of the reservoir, and then double click at the junction. And you'll see how it's continuing to draw. I can terminate that just by pressing the escape key on the keyboard. All right, so I've got junction connected to reservoir connected to junction with the pipe. Any questions so far? All we've done is drawn a line. But these lines and what's at either end of the line represents things and can be assigned characteristics. And in the background, this computer knows not only the hydrostatic equation, but it knows some other equations as well that allows you to calculate energy loss due to pipe friction. Let's use this select objects cursor and double click on the pipe, because it'll bring up this dialog box here, and you'll notice that there are certain things about the pipe that's already known. It's given the pipe a name, like it's just calling this pipe 1. We could call the pipe anything else. We could call it hose, or we could call it pipe A. We could name it whatever we like. It knows the start node and the end node. And the start node is this reservoir. It was the first place that we clicked. The ending node is the downstream junction, which is the second place that we clicked. So it's keeping track of what's at the end of each pipe, the other objects in the system. It knows the length of the pipe, and right now the unit system that it's in, you can see from the screen it says GPM. That's gallons per minute. And so if it's going to be using flow rate units of gallons per minute, then that means the other units are also traditional. So length is units of feet, diameter is units of inches. Okay, so in the handout we have some characteristics of the pipe that are known. It's 175 feet long and 3 inches in diameter with a roughness coefficient of 110. So let me change all these parameters so that it matches up. The length is 175 feet. The diameter of the pipe is 3 inches. And the roughness coefficient is 110. The roughness coefficient is just something that is used to calculate the effects of pipe friction. You know how pressure would be decreasing in the direction of flow because of the effects of pipe friction? This roughness coefficient helps the computer to calculate how quickly the pressure would be going down. Okay, so we assigned some characteristics to the pipe. Let's next click on the junction and see what pops up when we double click on the junction. Okay, so there's another dialog box here that has junction ID, it has the coordinates. You could give it a description or a tag of some sort. The things that have a star next to it are the required details. And so the only thing that this has to have is a name and an elevation. And so by default, the elevation it assumes is 0. But from the handout, we know the elevation of the fountain is 588.36. So let me assign that elevation in the computer as well, 588.36. Okay? And I could change the name. Instead of 2, I could call it fountain. All right, so I've updated that. let's look at the pipe. Over here in the browser, I've just changed it from junctions to pipes. Okay. Look at what it's changed. When I changed the downstream ending node, when I changed the name, it automatically updated the pipe characteristics. And so when I called that junction fountain, now the pipe knows it as well. The pipe knows that it starts at 1 and ends at fountain. So that's nice that it's dynamically updating that in all of the places that it would apply. Okay, let's over here in the browser now take a look at the reservoir. Okay, so that's the same thing that would happen as if we had double-clicked on the reservoir itself. It just brought up the characteristics of reservoir. The reservoir ID is 1. Let's call it reservoir. Because why not? The required thing that it wants to know is the total head. What it's really essentially asking is what's the elevation of the water in the reservoir. And remember this word head, the technical interpretation of that is it's the sum of 3 terms. It's the sum of the elevation of the water, the pressure head of the water, and the velocity head of the water. And so in a tank, where a reservoir is essentially a really large tank, when you have water that is at the surface of the reservoir, it's not moving anywhere. Like even if the water level is going down slightly because the reservoir is being drained, the velocity that it's falling is so minuscule that we can effectively neglect the velocity head. And where there's air above the reservoir, where the water at the surface is in contact with the atmosphere, then that means that the pressure is effectively 0. So the head is the same thing as the elevation. The other place we've talked about head was when we were discussing piezometers. And we talked about how if you have a pressurized pipe, when you have water flowing through a pressurized pipe, and if you wanted to get a sense for how much pressure there is, you could puncture the pipe and water would start spraying out because it has pressure. But then instead of allowing it to spray all over the place, if you confined it with a piezometer, the water level would rise to a certain elevation that is reflective of what the pressure in the pipe is. And so I talked about the pressure head. And that is how high did the water level rise in the piezometer as a result of the pressure in the pipe. So that's another place you've seen this word head before, was when we were talking about flow-through pipes. Okay, so the total head in the reservoir is just simply going to be the elevation of the water surface. So let's type in 675.47. Here in yellow are parameters that could be calculated by the system. So we're not able to enter data into those fields. They're calculated by the system. Okay, so I'll pull up the junction again and look at what it says for the pressure of the junction. It says not applicable. And the reason why it says that is it hasn't actually calculated anything yet. This lightning icon, run, when I click on that, it's going to calculate the pressure in the junction. So let me do that. I'll click on it. Okay, run was successful. And it calculates the pressure is 37.74. And how does that compare to the pressure that we calculated? It compares pretty favorably, because what we calculated was 37.75. Probably the difference is just that it knows the unit weight to a greater degree of precision than we used in our calculations. I think the unit weight of water is actually 62.37 pounds of force per cubic foot. So it's right. The computer's right. So that gives us some more confidence that it can be trusted, at the very least, to do the hydrostatic equation. Now what it's actually going to do if we start to enter in demand is it'll use the hydrostatic equation and also some friction loss formulas. Here where it says base demand is right now the 37.74 is what the pressure would be if the fountain wasn't turned on. That's just how much pressure is in the fountain before any water starts flowing through the pipe. But what would the pressure be if we started to withdraw 50 gallons per minute from the fountain? So remember here the units, GPM, that's our flow rate. So here for base demand, I'm going to put 50. And this is going to be simulating how does the pressure change if there's 50 gallons per minute withdrawn from the fountain. Okay, now when I press enter, it doesn't change the pressure yet. I have to click on the run button in order to find out what would the different pressure be. So I click on that. Okay. It takes the pressure down to 36.87. So that's not so bad. We only lost a little bit of pressure. What if I took the demand up to 200 gallons per minute? Then what would the pressure be? Okay. Oh, down to 26.36. So we've lost quite a lot of pressure now, about a third of the available pressure when we're trying to get 200 gallons per minute out of the system. Well, what if what we actually need, the fire department says we need to be able to withdraw 500 gallons per minute from this network. So let's simulate that. And not only do they want 500 gallons per minute, but they want some positive pressure, a certain amount of pressure to allow the water to flow into the truck so that it can be sprayed on the fire. So 500 GPM. What would the pressure be at 500 GPM? Run. Oh, we got a warning message here. Warning messages were generated. Negative pressure. Look at the pressure it's calculated. Negative 24.37. That's an indication that it's not possible. With the 3-inch pipe that we have, you can't get 500 gallons per minute with the pressure difference, with the water coming from this elevation. We either have to make the reservoir higher so that there's more energy to force the water through this tiny little pipe, or if that's not a possibility for us, if we can't change the elevation of the water surface, then we just have to make the pipe diameter larger. So let's try that. Let's try making the pipe diameter larger. So I'm going to click on the pipe, and here where it says the diameter is 3 inches, I wonder if just going from 3 to 4 inches would be enough. So I'll change it to 4 inches. All right, and I'll run. Run was successful. We didn't get an error message. That's a good sign. Let's pull open the junction report and look at the pressure. 22.45. So we've got a fair amount of pressure there. We're getting the 500 gallons per minute. And what you've just seen is that iterative process of optimization that is a huge part of what engineers do. Trial and error, making an initial design and then updating the design to reflect the criteria. And remember that what an engineer wants to do is make the smallest system that will meet the system's requirements. So we want this system to just barely work. Like we wouldn't want to have a 12-inch pipe if a 4-inch pipe is good enough, because using a 12-inch pipe would cost a lot more for excavation, for materials, for installation. It would just be a more expensive system. So you've probably heard the phrase before that anyone can make a bridge that works, but it takes an engineer to build a bridge that just barely works. And that's what you want. You want the bridge to just barely work. You want the beams to be just barely thick enough. You want the capacity of all of the elements of the bridge to be just good enough, but not a lot better. Because if you're overbuilding something beyond what's needed, then you're essentially wasting the money of your client. Of course, you got to build in a safety factor. You have to make sure that all of your bases are covered. But once you've defined what the criteria is, like what's the requirement, you meet it, but you don't exceed it. Okay, so in this case, I've just showed you a little bit about the relationship between demand and how that changes pressure. On the back side of your handout, it has a series of 10 questions, and you're going to answer those questions for this week's lab. This week's lab is not a full report. It's just a response to each one of these questions that you should embed into Microsoft Word. And let me show you a little bit about what I mean. So let's change this back to the baseline condition. And the baseline condition is there was no demand. So let me run this again. Oh, I need to change it to no demand, and then also I need to change my pipe diameter back to 3 inches. Okay, 3 inches. Okay, run. Run was successful. And let's look at the reservoir. I'm sorry, the junction. 37.74. I'm going to press, there's a button on my keyboard that says print screen. It actually says PRT SCN, and it means print screen. So I'm going to push that button, and let me start up Microsoft Word. All right. Okay, if I do paste, it's just going to paste a screenshot of what I had on my screen when I pushed the print screen button. That's pretty convenient. And I'm going to crop this image a little bit because otherwise some of the text may be a bit small. So I'm going to click on the format here and crop, and I'm going to move these so that it's just showing the part of it that I'm interested to depict. All right, so now I can make that a little bit bigger. All right, so this is the baseline condition using the given elevations, fluid properties, and pipe diameter. All right, now look at question 1 on the back side of your handout. It says, what would be the pressure in the drinking fountain? Let me actually bring it up here. All right, what would be the pressure in the drinking fountain if the system contained 120 degree Fahrenheit water instead of the 50 degree Fahrenheit water that EPANET assumes by default? Does anybody have the textbook today? Anybody have the textbook handy? Does anybody have access to the electronic version of the textbook? No? All right. Table A5 would be able to tell us the density of water at 120 degrees Fahrenheit. Let's see if we find it somewhere else. Water density by temperature. Engineering toolbox. Well, all right. Boom, there it is. 61.71 pounds. Oh, that's pounds of mass. That's fine, because pounds of force is the same. 61.71. Okay, so let me put on my mask because I'm going to be going over here to the other whiteboard. Oh, it's already here from the last class. 61.72 is the unit weight at our temperature of 120 degrees Fahrenheit. 62.4 is the unit weight at typical conditions. Okay, so the specific gravity of that, does anybody have a calculator handy and can do 61.72 divided by 62.4?
0.989.
Okay, thank you. So this is specific gravity. Okay, so what question 1 is asking us to do is change the program so that it knows a different fluid. The place that you can do that is here under Project Analysis Options. And under Project Analysis Options, one of the analysis options you can change is the specific gravity of the fluid. So right now it says the specific gravity is 1, but if you said it's 0.989, it's going to assume that whatever's this fluid flowing through the pipes is a little bit less dense than water. So this could be representative of our 120 degree Fahrenheit water. So if you click Run, Run was successful, and we pull open the junction. Now it's going to be a different pressure. Okay, so I'm going to press print screen, and then question 1 was asking what would be the pressure in the fountain if it had 120 degree Fahrenheit water. So 1. If the water in the system is 120 degrees Fahrenheit, then the pressure in the system is, what is it? 37.33 psi, as shown in the screenshot below. Okay, and then I'm going to paste in that screenshot as proof that I actually did it. And let me crop this, because in cropping it gets rid of the stuff that's extraneous and focuses in on the important stuff, and there's my proof. So that's the answer to number 1. And if you look, the rest of the questions in this assignment basically just take you through the process of changing some parameters and observing what it does. Some of these you'll just post a real short answer and a screenshot. Others of them is explanations. So here it says, write a brief explanation about 1 paragraph about the pressure difference that was observed in problem 1. Explain why it was different and explain the directionality of the difference. So what I'm asking you to do is explain why warmer water changed the pressure. So some of the things that you might answer is that when water warms up, it expands. So a given mass of water expands to occupy a larger volume, which that effectively reduces the density of the fluid. And if the fluid density is decreased, then for a given height difference, for a different delta H, if the unit weight is lower, then the pressure change would be lower. So go through and in words kind of explain some of the foundational principles. And, go into some detail. Typing is quick. You've got some time. So this word directionality must be important because it's bold and it's underlined. I'm trying to draw your attention to the fact that I want you to point out that the pressure decreased. So don't just say something is different than it was before, but say, like, what direction did the change go? So decreasing the specific gravity decreased the pressure, and explain why the pressure got less rather than larger. And this word directionality, I'm going to emphasize a lot this semester, because I'll want you to interpret your lab report results in such a way that you are telling me not just like what was the percent difference, but beyond that, you should be able to explain why the observed values, for example, were less than the predicted values. Was there some specific thing about the equipment or the water? Was there some specific error that may have been made that made it so that the calculated or the observed results were greater than or less than? So it's not just enough to say that they were different, but try and piece together a logical scientific explanation for why it was the direction in change that it was. Okay, so that's what I've got for you this week. Questions 1 through 9, all of the conditions, questions 1 through 8 is just thinking about static. There's no water actually being demanded from the junction. But then in question 10, you can actually start to increase the base demand, and you're looking for a water pressure of 55 psi. What is the maximum flow rate if the discharge elevation is at 590 and if you must, okay. So I give you an elevation, a required pressure, pipe characteristics, and you're trying to determine how high can the flow rate go to still deliver the pressure that's required. So Question 10 is kind of an iterative problem that you can solve by changing the demand and calculating the pressure, changing the demand, calculating the pressure over and over again until you hone in on the maximum flow rate that gives you still 55 psi. All right, so any questions I can answer about what you've seen so far? If you'd like to stay here in the room and start working on the assignment now, I'd be glad to stick around with you. If you don't have a computer today or you'd rather do this assignment later, then that's fine too. You can definitely take off. But I'll post this recording on YouTube in case you want to see certain places that I clicked or how I got into the menu for a given thing. I'll put that up online today. And of course, if you have any questions, feel free to contact me. I'll be happy to help you out. All right, that's it.